So, and welcome everybody to today's webinar. We are talking today about the universal concrete architecture. This is the fourth webinar in a row, and my name is Konstantin Kersten, and I'm joined today again by my colleague Wendelin Arnaudov. We're both from Process Software, and Wendelin will later on go into the details of the concrete architecture. Yeah, and after, let's go one back, after he did his presentation, there's time for discussion. Yes. If you want to know more about what we are talking about today, you can always check the deliverables for the project, for the reference model, the architecture, reference architecture, and the concrete architecture. We provided the link here, so we're going to put the presentation also on YouTube, so you can have a look at that as well there. Then we have earlier webinars. You find them in YouTube under the channel Project universAAL, or you can also go to the universal.org website. There you have all the events that we are going to do, that Universal going to do, and links to videos, training material, source code, everything you would expect. If you want to be even more involved in universAAL, then we would like to invite you to join AALOA. The AAL Open Association, and it's promoted by the partners of the European integrated projects like Persona and Universal, and the goal is to maintain the source code and make it available. So if you want to know what's going on in Universal after the project has ended, you should head out to AALOA. Okay. Then I think without further ado, I will give to Wendelin, who is going to present the concrete architecture for you.
Hello, my name is Wendelin Arnaudov. Working for Process, we are partners in universAAL, bringing there our experience on middleware and ORGI. And today I'm going to present you the details of what we have decided and specified in the project regarding the concrete architecture for AAL platforms. As Konstantin mentioned, we have provided a document, deliverable, describing everything in details. Also, you can find a reference documentation handbook or developer handbook available online. So, if you have questions about details, if you want to see how the things are done with source code, snippets, etc., please use these two sources. So, what is universAAL? We are talking about this. This is a research project focused on AAL services and emphasis cleaning services, and we would like to provide an open and scalable technological platform that supports the whole life cycle of AAL services, from development to deployment and distribution of these services. We would also like to provide to support widespread acceptance and adoption of this platform. As I mentioned, this is a research project that is going to its end in a month, and most of the things are already done and available on the website. So now we have the standard scenario where we have the key user or beneficent of the platform. This is the assisted person. This could be an elderly person or disabled or anybody else that needs some help at home. He is residing some location, his home, and there we provide our specifications. We deliver the hardware in order to provide the service that he needs. The service originates, of course, by some provider that develops the software part or the application. So we in the project are dealing with the tools that are needed by the developer for building an application, testing it and deploying it and storing it to some developer community. All these services can be packed and presented in a kind of application store, our universal store or U-store, where the service provider compose the services out of different applications, pack them with hardware and human resources, care personnel, and offer all this to the end users. Out of the U-stores, bundled services are deployed on the runtime platform. So these are the three key platforms that we have in the project: the runtime platform, the development platform, and the community platform or U-store. Moving further, we are talking now about the concrete architecture of AAL. In the project, we have passed through several stages. In the first, we have defined the reference model that provides a common understanding of the area. Then we have derived to the common approach of the software development in a reference architecture that provides a broad area of integration and communication with other architectures, and it's a kind of template blueprint for further architectures. And out of this, we derived into concrete architecture. Here we provide a specific solution, instantiation of the reference architecture. When we are talking about the instantiation, this is what we want to do is we are trying to implement specific architecture issues by decomposing into implementation specific components and by identifying actual relationship from high-level relationship provided the reference architecture. The instantiation process from the reference architecture to concrete architecture includes several steps. A few of them are identification of significant components with components responsibilities, interactions, control, data flow, etc. The instantiation process also identifies the non-functional architectural concerns like security, reliability, other cross-cutting concerns. From the reference architecture, high-level services to different stakeholders and high-level interactions among them, the instantiation process begins with identification of significant services. The specification process includes comparing and analyzing the experience of previous research projects in that area. Konstantin mentioned Persona, and also there are other like Soprano and Power, whose experience have been analyzed, and it was used by building and specifying the architecture that we are going to present. Out of the use cases of all these projects, we have identified few that we call them reference use cases, and the work on the architectural specification is focused or centered around implementation of these reference use cases, and we are talking about reference services in the reference architecture specification. So, what we are going to talk today is we are going to consider the concrete architecture of these platforms that I have displayed earlier with persons and stakeholders. The runtime support platform, where the applications are running and actually it's providing its service to the assisted person. The development and community support platforms that are aimed to help the developers and service providers and to facilitate them providing the services offering on the application store. Here we are going to consider a few models. For example, the composition model, that is identification of main building blocks presented as component diagrams. The collaboration models describe the interactions between the components, normally presented as sequence diagrams. The information model talks about the data model, the information that is exchanged, and here we have ontology models that are presented as RDFs. And then the next we have the mapping between component and interfaces. So this is the component interface specification model. We are going to mention the key design decisions that were made in the project. When we are talking about decomposition of the system, I would like to go to the abstract building blocks. On the top level, you see the top level platform components that we talked about. These are reference support platform and the tools related to this platform, the developer support platform and tools, community support platform and tools. The red area is what we are going to discuss in the next minutes, more specifically the concrete architecture of the reference support platform. Here we have expert groups that are dealing with specific components and building blocks, while the other platform components, as runtime support platform, developer, community support platforms and tools, would be discussed in the second part of this webinar. I mentioned that in the decomposition model we are going to talk about component diagrams. In these diagrams we have identified the main building blocks and interfaces, explicit interfaces between the building blocks. The lines that you see here have a meaning. The colors used for the arrows identify the communication with the buses. For example, the blue lines are for the service bus, the green for the context bus, and the red is for the UI bus. What are these buses will be seen in the next slides. So in order to make it easier to handle, to group them, and to compare the inputs, information from the input projects, we have introduced the layered model. We have three basic layers. The node middleware layer that attempts to abstract the different physical nodes underlying hardware and platform and provide unified interfaces for the other components to operate on, be deployed and run there. The buses are also there. This allow the communication, execution of services, and data. Then we have a number of managers that could be considered as level components that communicate with each other and the other components through the platform facilities or the buses. So these are like applications also. Here we have the core managers that are required for the platform to run. However, they can be omitted in some nodes if they are already presented in some other nodes in the space. The pluggable managers are required for the platform to run with all its advanced features, but the basic underlying capabilities would still be available if none of these were presented at all. And the optional managers are not required for the platform to run or provide its features, but they add the advanced features and interoperability. In this sense, these are like applications and share the same layer. You see that the internet is also presented here. It's not a layer, it indicates the area that is outside of the space. And components in this area are located in some external server. I mentioned space. If you remember or if you refer to reference architecture, this is a term that describes all platforms, runtime platforms that are put in one location and allow the distribution of the system. So out of these layers, we'll see the different expert groups, the same components, again, with highlighting the expert groups. We are talking about the middleware expert group. There is a building block for the reliability of the middleware. It extends the work of the middleware itself because the purpose of reliability goes beyond the basic functionality. We have user interactions building block, expert group, the services provision expert group, context management expert group, security that is stretching through all layers. We have local devices discovery and integration expert group or LDDI, and remote interoperability expert group that deals with communication between the different AO nodes and sharing the functionality with external worlds. Moving further, this slide presents the middleware expert group components. Here, as I mentioned, the middleware extends the native system layer of the different physical nodes participating in the AL system, hiding distribution heterogeneity issues from the layers above. The key building blocks here are the container building block that represents the capabilities needed for integrating independently developed models within one single execution environment in order to facilitate access to locally shared APIs. Or in other words, it's the software over which the runtime support platform runs. Example of such containers used in universal implementations are ORGI and Android. Discovery and peering building block since the middleware instances are running on different nodes in one AO space, it's supposed that these nodes should communicate somehow with each other. They should discover each other and establish peer-to-peer communication channels. This presupposes the existence of the next building block or the communication building block. After the discovery and peering block discovers and interconnects all already nodes, these nodes will be able to exchange messages towards becoming a self-organizing ensemble. The role of this building block will then be established to establish a messaging and communication model that allows hiding the distribution and possible heterogeneity of the ensemble. The data representation block Its purpose is to provide an implementation of both RDF and OWL with support of injecting ontologies or data models. Specifications for RDF and OWL by W3C predefine the needed features, so representation and serialization. As I mentioned, the reliability building block, this extends over the middleware expert group, and its goal is to improve the reliability aspects of the universal platform. That's why it's in vertical layer, cross over the other layers, especially the middleware. This can be done by dealing with major challenges of reliability and enhance the system efficiency, time-triggered Ethernet extension model, testing model, error detection model, fault tolerance model, etc. Then I would like to present you the building blocks of the context expert groups, starting with the context building block that is it's supposed to provide the adequate communication with both push and pull based between providers and consumers of context data according to a common model for the representation of such information. The key component here is the context bus. It is built on the middleware providing publish-subscribe mechanism for peers via space, where they can forward context events built with ontological descriptions. The context storage stores events forwarded through the middleware, could be retrieved, searched for. It allows access to this data by several methods like retrieving events stored from the context bus, or between some timestamps, some criteria. The reasoning for maintaining the current status context is also possible. Stationary reasonable is a general purpose reasoner that uses existing information from the context bus and builds up new contextual information, allowing management of the rules. Then we have Space Manager Tools building block. It manages the shared data representing user preferences and characteristics so that the interaction with the user is personalized and all components are able to interact. The platform provider's building block is a placeholder for provision of specific context data considered as basic or of common use. Those components that provide such commonly needed context data are common providers represented by this building block. So these are failure diagnosis reasoner and system information provider. Then I would like to present you the components of the service expert group. The service management building block is supposed to facilitate the service-based interoperability. It must handle the registration of services broker between service providers and consumers for handling service requests. That is by matchmaking between received requests and available offers, and provide for service composition and orchestration. For this purpose, a model must be provided that defines how services can be described, how service requests are constructed, and how workflows of composite services should be described. The registration facilities must provide for secure shared knowledge about availability of services. The key component here is the service bus. It extends the middleware by providing for service-based semantic interoperability. It defines protocols for provider agents how to advertise their service utilities by semantically describing them in service profiles and how to cooperate in the processing of service requests. It also defines protocols for requester agents, how to formulate their requests semantically in terms of goals that they want to reach. Finally, it resolved the mediation task by matchmaking between received requests and advertised service profiles. AO-based service orchestrator building block is based on the idea of supporting for service composition using an appropriate scripting language with a workflow engine and for executing composite services defined in those languages. However, the aerospace orchestrator should work on the basis of a novel scripting language that allows utilization the whole functionality available in the spaces. Here, ASOR, this is the aerospace orchestrator, is the component that manages the configurable database of installed scripts and start the interpreter to run such scripts in a situation-aware way. Moving to user interfaces expert group, we have a UI framework building block that addresses the challenges related to explicit interaction between the AL spaces and the human users. It must provide for independence of applications from the concrete I/O infrastructure or set of concrete I/O channels available in the AL spaces. Here we have a UI bus that enables communication between the applications that need to reach human users and the UI handlers. This bus is call-based bus without any support for synchronized delivery of replies. It defines protocols for suspending and resuming dialogues. The dialog manager is the main component for handling system dialogues. It represents the whole system by providing different flavors, system menus, managing system reactivity, and handling context-free user inputs. It assists the UI bus by acting as a representative for the framework supporting context awareness, personalization. The resource server provides resources, audio, images, etc. for the UI handlers to be used. The resources are retrieved from the common universal configuration directory through HTTP requests. The common user interfaces building block we assume that the separation between presentation and application is achieved by the UI framework. UI handler can be added, removed, or replaced dynamically and freely. So this building block would contain all these handlers represented as a generic single component. Here is given one such UI handler. This kind of major component would be responsible for capturing human input and presenting system output to humans in an application-independent way. For example, SMS handler, web handler, etc. Moving to the next expert group, this is the remote interoperability expert groups, and here we see in the building blocks the goal of this expert group, as mentioned, was to realize the communication, to support the communication between one AL space and the external world. The key component here is the AL space gateway building block. It addresses the challenges related to interaction between the spaces, the external world. It should provide the necessary interfaces for accessing the AL space resources from outside, and also importing services outside the AL space to be accessible by the components in the space. Additionally, it must provide connectivity between two different AL spaces for accessing remotely bundles and data of one AL space. The ASG gateway is responsible for communication between two aerospace gateways, and it provides the needed level of connectivity and exchange of functionality and data between the two aerospaces. It allows the remote invocation of bundle that belongs to different aerospace. The connection is made between the ASGs of each space through the internet. With the remote invocation, the aerospace can have access to functionality data that run and belong to other aerospace, thus extending a lot of the functionality of the solution, making more distributed. To this building block, airspace gateway building block, belong also the proper exporting and importing subcomponents that are responsible for the relevant tasks for introducing external functionality to the platform and also publishing the existing functionality to the external world. The remote administration building block contains tools that allow the remote access to the aerospace in order to manage the data in such space by service providers. Here we have a profile agent that takes care of synchronizing the user profiles between the data stored in the view store and the data stored in the context store of the aerospace. The remote interoperability tools building block contains tools that are designed and implemented under the scope of this expert group and provide support for interoperability issues. Currently, only one such support tool has been devised. The ontology repository is constructed to support universal requirements identified by defining a threefold knowledge representation paradigm: subject, predicate, and object. Moving further to local devices discovery and integration. We are aware that not all hardware that is available in one aerospace is suitable for running universal or AL middleware on it. That's why we provide means for integrating such hardware in universal. And this is the task of this expert group. And here we have the building blocks that provide functionality that overcome the diversity of different systems and devices and help to integrate them based on the common service representation of the middleware layer without much effort. Usually the AL-aware wrappers or adapters are used to bridge such subsystems with other AL-aware artifacts. So we have here three main components that represent different layers that are supported. The base driver component is usually composed of a number of technology drivers, sometimes already integrated in the operating system with well-defined APIs like Bluetooth, sometimes written from scratch or with ad hoc solution if standardized APIs are not available, like Zigbee, Connex, etc. It takes care of interfacing with actual network hardware. Then we have refinement driver that represents the abstraction layer. This component transforms the underlying proxies that are a flat and raw representation of the physical network nodes installed in the environment to more significant device objects, which are easier and with easier and intuitive interface for the developers. So this layer is another set of proxies that refine the proxies associated by the access layer. the lower layer, and it can be quite complex with different kinds of transformations obtained by combining the original information in several ways, aggregating, splitting, filtering, etc. On the top of these two layers, we have the integration layer that is provided by the exporter building block or adapter. This component publishes the proxies that are instantiated in the abstraction layer by creating new endpoints according to specific universal communication mechanisms. Multiple endpoints can be created for each sensor, thus providing multiple ways of integrating the sensor network. And it communicates directly with the buses, service bus, context bus. So in this way, representing the device that is connected and integrated. Further, we move to security expert group. Here we have some standard things like crypto utilities that provide features for encrypting, decrypting any given piece of data according to the some setup of encryption options. Consent utilities that takes care of composing consent documents, which can be used as standard representations of authorizations by a user to let a third party manage their data. Authentication, authorization should be also handled by the appropriate components. Moving further to the next kind of model, system collaboration model. As mentioned, these describe how the connections between the components react and how their interactions take place. One way of representing this is by use of sequence diagram. In the runtime platform, these sequence diagrams are quite straightforward because it's completely software-based. You have seen the interfaces between the components, so most of them are self-describing. Here we can show some sequence diagrams that are very important, are representative for the platform. Due to a lack of time and space, we are not able to cover them all, but you can refer to the deliverable that was mentioned in the beginning. The link will be also presented at the end for more details. For example, we have here the context management building block and the feature or the use case of publishing and receiving events. Any universal component can register to the bus. At startup time, both context publishers and subscribers. Using the context publisher, it can send context events to the bus, and then any event from the bus that matches the registered subscriber is delivered to it. And you can see both the sequence diagram or the diagram on the right side. Here we have two context subscriber applications, S1 and S2, as well in the chain that is context history entrepot, or this is our context storage. They register context event patterns in the context bus, and these specify to the bus which context events the two applications would like to receive. These are marked with number 1. The context publisher application P1 register context event pattern 2 to the context bus. So in this, it specifies what type of context event messages it intends to publish. The blue box in number 1. The context publisher application P1 then sends a context event message to the context bus using its publish method. Number 2. The context bus receives the context event from the context publisher P1 and checks in details against all context event patterns that are currently registered. It finds that the context event pattern registered by the context subscriber S1 does not match the details of the context event sent by the publisher P1, but that the context event pattern that has been registered by the subscriber S2 does match the details. So as a reaction to the positive match, the context bus sends one copy of the context event to the context subscriber S2 by calling hello context event method. This is step 4, and the context subscriber S2 has received the context event that was sent by the context publisher P1 and can now use this information in its further computations. Very similar is with the service management building block or handling a service call. Here we have the communication between the service caller and service callee. It takes place over the service bus. Both bus members, caller and callee, register the bus. So in our case, in step 1, we have two service callees or providers, E1 and E2, that register service profiles at the service bus. They use this to specify to the bus which services they intend to offer. Step 1. The service caller application R1 or requester sends a service request to the service bus in which it states what kind of service it requires another application to perform. This is step 2. The service bus checks the service request from the service caller R1 against all service profiles that have been registered by the service callees. It finds that both the service callee E1 and E2 are capable of performing the requested service. So this is handled by the service bus, and thus forwards copies of the service request sent by the service caller to both of them. At this stage, it is no longer a request, as some real services have been found and will be explicitly called. Hence, the object they received is not an instance of the class service request, but the class service call. This is the step number 4. The service callee E1 quickly performs the requested service and sends an appropriate service response back to the service bus, step 5. The other callee E2 fails to perform the requested service within the available time frame, possibly because of application termination or interrupter connection, etc. So we see this red cross that marks the termination of the service. Based on this, the service bus aggregates the service responses from all services it has called, in this case only the service call E1, this is steps number 6, and sends the aggregated service response back to the service caller, one, the blue box, and also notifies it that another service callee failed to respond to the request in time. On step number 7. Very similar interaction appears when communicating with external world. Here we have the AL space gateway that is mediating for the communication and acting as a transformer of the request. Moving further to LDDI building block, provision of services. Here we have a description of how a request is going through all the layers of the LDDI. So a call issued to the service bus addressed to a matching service of device provided by an exporter is answered by this exporter and delegated to the refinement driver through the container communication facilities, and this does the same to execute the actual call to the hardware driver. Very similar is done with events, sensor events, with the other direction. We have an event from the base driver as an OGI service that is sent to the refinement driver, and then to exporter, and at this point, the exporter uses the context bus, the middleware facilities, to share the information to the other participants of the platform. Moving further to the next information model, next system model, this is information model that deals with the data model and the ontologies that are describing it. It's used to describe the data model that is transferred or managed by the interactions described so far. The relevant part of this model is ontologies that compose the root resources that are exchanged across components. Here we are dealing exclusively with resources. Two different groups of these ontologies can be observed. The basic one, embedded into the building blocks themselves, which describe the root concepts used in the interactions. For example, resource, service call, context event, etc., service pattern. This is an essential part of the platform operation. And the second group of ontologies is modularly plugged into the platform thanks to a data representation block to represent different domains of semantic data models for use of the managers and applications. The ontology diagrams are pretty difficult to read. That's why I'm not going to present all the details here on these small screens. If you refer to the documentation, you have nicely cut and separated sections of the diagrams. But here I would like to present the root data diagram. The following diagrams provide an overview of the relevant classes of the model of data representation building block. Here the green classes denote the RDF concepts, while the remaining parts are OWL concepts. The yellow classes on the left are designed to define an ontology and manage ontologies, and the gray classes on the bottom right are implementation of some very basic concepts that can be used by different workers. Moving further, an example of a very complex ontology diagram, the service ontology. The service is represented as it contains a model of the service processing, and this model is the representation of both the service being provided and requests to invoke them. The next diagram represents the user interface building blocks and the interactions and the ontology and different components, model, resources, and dialogues, text area, and etc. that are pretty familiar to many people. Dealing next to the context building block, it represents the context ontology. The context plus component contains the meta model of the context information itself. That is the part of the context modeling that concerns to context data sharing. In other words, the ontology of the context events and all its related context concepts and metadata. The reason for this is that this model is tightly related to the operation of the bus itself. Moving to the next ontology concepts, we have several specified and implemented by universAAL: physical worlds, ontology concepts that are dealing with shapes, different shapes, physical things, locations, building related concepts, others, etc. Then we have units ontology that represents the different units of measurement in universal, such as units or dimensions. Since this is a common concept that can be used by any other extending ontology, it's considered part of our ontology. The measurement ontology represents the different measurement capabilities in universal, such as measurement, signal, measurement error, etc. We have another ontology. This is the profiling ontology. It covers the concept needed originally by the user model building block, but adds a twist to its final purpose. Not only it models users and their profiles and their characteristics, but also any other basic concepts which characteristics are of interest to the universal platform. The AL services and the AL space themselves, physical things, etc. This way, the ontology is dedicated to model profiles of things that can be further described for these profiles and further sub-profiles. So, moving next to the component and interface specification models. In this, we have class diagrams that list the interfaces that are attributed to different building blocks and interfaces realizing different cooperation models. We have also use case diagrams showing the use cases and the use cases of each block. Of course, here we have a great number of components and resulting diagrams, lots of interfaces, and I'm not able to go in details for all these interfaces. Please refer to the documentation that is provided in the beginning of this webinar. So, for example, we have here the discovery and peering features and the use cases. You see the blocks and the features that are realized by the different blocks. Then we move to the next pair of platforms. After we have finished the runtime support platform, we are going to deal with the development and community support platforms. They also have been described using the same models approach, and I'm going to start with a relation to a reference architecture. This is a diagram that is very familiar to the one in the beginning, where we have the top level components of the reference architecture and the top level components of the concrete architecture. So the AL Studio is the client side that is provided to the developer for developing its own application. It contains lots of wizards. The Universal Control Center is facilitating the deployment and configuration of applications onto the runtime support platform. The U-Store is an online application server, that offers services that can to the end users, while the developer depot is a server-based component storing different utilities, binaries, ontologies, and resources for developers. On the next diagram, you can see the relationship between these components in a component diagram. Moving further, you see the subcomponents of each of these components. Most of them are self-expressing. For example, external services integrator, web server, catalog, etc. Then we have in the system collaboration model the interaction or collaborations between each pairs of these components. For example, in this one, we have the AO Studio that collaborates with the developer depot in order to make resources from the depot easily available to the developer. AO Studio uses the Maven repository of the developer depot to access the binary version of the universal platform and uses the HTTP server and Subversion repository to access the list of examples and import. The Eclipse update site, which is used to install the AO Studio in Eclipse, is also available through HTTP server of the developer depot. The AO Studio also uses ontology repository of the developer depot, etc. The next pair of collaboration, here we have the AO Studio and the execution environment, and the AO Studio can launch the execution environment and run and debug AO applications there. Moving further to AO Studio and UStore, the collaboration here is that AO Studio publishes the applications created by AO Studio on UStore. As shown in the diagram, there are two relevant interfaces published by the UStore, one for accessing the catalog of application categories and one for managing the applications to publish. The next pair of component is the UStore and the UCC. Here the Universal Control Center cooperates with the UStore in order to realize the purchase and deployment of AO services to the end user. As illustrated in the diagram, the interaction between the UStore and UCC is based on two interfaces. The UStore provides a service for accessing the online store, while the UCC provides a service for deployment management. The final pair is the cooperation between the UCC and execution environment. As mentioned, the UCC collaborates with the execution environment to deploy applications on one or more nodes in the AO space. UCC uses two interfaces provided by the execution environment. Through the AO Space Manager, matching peers for deployment of parts of applications are discovered, while the Deploy Manager interface is used to perform the deployment on the platform. Moving to the system information model, the main information that is shared between the components is the information describing the services themselves. By service, I mean the bundled service. In Universal, we define Universal service as a composition of software application, hardware device, hardware part, and human resources. So the service that the assisted person receives can be executed by the software. He can interact with some sensor devices, or he can use the help of some care personnel, human resources. So this is described in this model. We have the application part, the software part described here. It presents the file structure, it presents the descriptor of the application, though Here we have a reference to the profiles, supported ontologies, information about the provider, etc. The next entity that we are going to present is the AL service itself in the bundle. As I mentioned, this could be a composition of different applications with hardware and human resources. It also provides the file structure and the descriptor of the service, while the application is developed and described and bundled by the developer using the AL Studio, supposedly. The AL service is composed by a service provider using the tools of the uStore. So the service provider selects pieces of components that needed to be included in the service, which software application, which hardware devices will be included there. The uStore takes care of resolving dependencies and capabilities issues, compatibilities issues, sorry. And at the end, we have this bundle that is made available to UCC to be deployed on the execution platform. Based on the information there, it is extracted, content is extracted and deployed. The information description is parsed to the ontology in order to be handled more properly. Here I give an example of the component and interface specification model. You see the different components, and in this case, this is only the uStore and the subcomponents of the uStore with their interfaces. Such diagrams are available for the rest of the components. And with this, I think we are done with the difficult part, all the details and diagrams. I would like to mention the key design decisions that have been made during the work of the specification group in universAAL. This is that we would like to have our own middleware for abstracting the underlying platform native specifics, and in this way make universAAL portable on great number of platforms and devices. And we have data model based on ontologies. For our reference implementation, we are using Java programming language. It's also part of the corporate architecture and the developer handbook, the examples. OSGI is used as a reference container for the runtime support platform. IBM WebSphere e-commerce is used as a core of the uStore with additional extensions and plugins that were developed within the project in order to satisfy the requirements of the project. And as I mentioned, Eclipse several times, our AL Studio is represented as plugins for Eclipse, Nexus, and Maven repositories. So, in this, we have seen the description of two groups of platforms: runtime support platform that is used for running components, and the development and community platforms that are used for development and provision of the services applications. These have been observed through 4 models: system integration, system decomposition and cooperation models, as well component and interface specification model. As I mentioned, the documents providing full information of the concrete architecture are available. The link below provides a link to the deliverable itself, called Universal Reference Architecture. It covers both reference model, reference architecture, and concrete architecture. And in Universal Forge repository, you can find the developer handbook under the link of reference documentation. For further information, you can visit Universal website. If you have questions, you can ask them now, or if you have further interest, you can book a training course. You can get a presentation. As mentioned earlier, the ALOA is trying to promote Universal. There is also another project for this, how to realize Universal, and so getting in touch with us will help you further with Universal. That was for me, and if you have questions, I'll be glad to answer you.
So first of all, thank you, Venelin, for doing this really nice presentation for us. We really appreciate this. And I think we don't have any questions at this moment. I would like to point out that if you want to dig in more, as Venelin already told you, we offer trainings. You're invited to visit YouTube to watch this webinar again. You can also watch all the other webinars we did there to get a more detailed feel for other parts of it, of Universal. And then I would like to take this opportunity to tell you that on Friday there will be another webinar, a short webinar, which will deal with the communities. So if this is interesting for you, please have a look at our Facebook page or our website to get the date, the exact time. I think it's 2 or 4 o'clock. Please have a look there. We will post the date there. And I hope you had fun, and wish you a nice time, and hope to see you on Friday again. Bye.